Have you ever stopped to wonder how your phone can just instantly find every single picture you've ever taken of your pet? Or, how a self-driving car tells the difference between a stop sign and a person? Well, let's dive into that, because the technology behind it is honestly one of the most powerful and, well, coolest ideas in all of modern AI.
Yeah, I mean, it really all boils down to a question like this. It's something we totally take for granted now, but how? How in the world does a machine, just a bunch of circuits and code, actually learn to see and recognize something as specific and, let's be real, as perfect as your cat?
Well, the magic behind all this is a really brilliant piece of engineering called a convolutional neural network, or what everyone just calls a CNN. It's a special kind of artificial intelligence that's built from the ground up to process and understand images, kind of like how our own brains do.
Okay, so to really get our heads around this, we're going to use one simple analogy for this whole explainer: Legos. Teaching a CNN to see is just like teaching a computer how to build with Legos. And here's the key: it doesn't start by recognizing a whole completed spaceship. Nope. It starts by learning to see the individual bricks, the simple little shapes, the lines, and the colors. So at its core, a CNN really has two main jobs. The first part is the feature extractor. Its entire mission in life is just to find all the different Lego bricks in a picture, all the basic little features. Then you have the second part, the classifier. It looks at all the bricks the first part found and gets to make the final call, saying, all right, based on these pieces, yep, that's a cat. All right, so let's dig into that first part. How exactly does a computer go about finding those Lego bricks in a picture? Well, it happens layer by layer in a really clever way. The heart and soul of the feature extractor is something called the convolutional layer. You can literally think of these as the network's eyes. This is where all the heavy lifting happens. Its job is to scan the image pixel by pixel and hunt for really specific, really basic things, like a straight edge, a sharp corner, or a patch of a particular color. So how does that scanning actually work? Well, the network uses this little tool called a filter. Think of it as a tiny magnifying glass that's only looking for one specific pattern. Let's say a perfect vertical line. This filter just slides over every single part of the image, and whenever it finds a match, ding, it makes a note of it on a brand new map, called a feature map. So at the end, you have this map that shows exactly where all the vertical lines are. And this is where that whole Lego idea really just clicks. The very first layers, they're just finding the most basic bricks, the simple edges and lines. But then the next layer takes those maps and combines them to find slightly more complex shapes, like a circle or a square. And then the layer after that combines those to find things like an eye or a whisker or an ear. See, it's building up from simple bricks into parts that we can actually recognize. Now you can imagine, after all that scanning, the network is just swimming in data. All these super detailed feature maps. It's a lot. And that's where the pooling layer steps in. Its job is really simple but absolutely crucial. It shrinks these maps down. It basically keeps the most important highlights and gets rid of the less important details, which makes the whole thing a lot faster and more manageable. And it usually does this in one of two ways. The most popular one is called max pooling. Think of it like a VIP section. For any little area of the map, it only keeps the single most intense or maximum value. It's only looking for the absolute strongest signal. Average pooling, on the other hand, is, well, it's a lot more democratic. It just takes the average of all the values in that little area. Okay, so the network has found all the Lego bricks. It's identified the ears, the whiskers, maybe a tail. The feature hunting part is done. So what now? How does it put all of that together to actually make the final decision and say, that's a cat? The first step is something called flattening, and it's a really important change in thinking. The network takes all of those 2D feature maps, the one for whiskers, the one for pointy ears, the map for fur texture, and it just flattens them all out, laying them end to end to create one super long single line of data. That one long line of information gets fed right into the brain of the operation, the fully connected layer. This is that classifier we talked about at the beginning, and unlike the other layers that were just looking at little patches, this layer looks at everything all at once. It weighs all the evidence and basically says, okay, I've got whiskers, I've got pointy ears, and I see fur. What does it all add up to? It's making the final global decision.
And at the very end, to give us a nice, clean answer that we can actually understand, the last layer uses a special function called softmax. It takes the network's internal scores and turns them into simple probabilities. So it doesn't just spit out the word cat. It'll say, look, I'm 85% sure this is a cat, maybe 10% sure it's a dog, and 5% sure it's a fox. And of course, the highest probability wins.
This all sounds pretty amazing, but it does bring up a pretty big question, right? How did the network know to look for whiskers or pointy ears in the first place? How does it get smart enough to make the right call?
Well, it learns pretty much the same way we do, through practice. A lot, and I mean a lot, of practice. It all happens in what's called a training loop. First, it takes a photo and makes a guess. That's called the forward pass. Then it checks its guess against the right answer and figures out how wrong it was. That's the error, or loss. And then, and this is the absolute magic of it uses that error to go all the way back through the network and just slightly adjust everything to be a little bit better next time. It literally learns from its mistakes, millions and millions of times.
Now, I gotta say, training one of these networks from scratch is a massive undertaking. We're talking millions of images and some serious, serious computing power. But what if you don't have that? Well, luckily, you don't always have to start from square one.
And this right here is a total game changer. You can take a powerful CNN that a company like Google has already trained on a giant data set. That network is already a world-class expert at finding the basic Lego bricks of our visual world. Edges, textures, shapes, you name it. You can just borrow its expertise.
And there are a couple of really cool ways to do this. First, there's transfer learning. Think of this like taking a perfectly built car engine and just dropping it into your new project. You don't mess with engine at all, you just freeze it and then train your own new decision-making part on top. This is perfect for smaller projects. Then there's fine-tuning. This is more like you take that same engine, but you also pop the hood and tweak a few of the last layers to get a little extra performance for your specific needs.
So when you think about it, from something as fun as finding your cat photos to something as serious as powering medical diagnostics or autonomous cars, these networks have basically given computers the gift of sight. And that kind of leaves us with one final, pretty mind-blowing question to chew on. Now that we've taught computers how to see, what are we going to teach them to look for next?